All right, we didn't get too much time on this in class, so I just want to walk you all through how you can derive the moment of inertia of an object using calculus. And it comes up every once in a while on the AP test. Usually they'll give you the moment of inertia, but every once in a while they want you to derive it. And when they ask you to derive it, it's not going to be a super difficult case. It's going to be usually a fairly simple case of a rod from the end or from the center or something like that. So here they want us to find the moment of inertia of a rod throughout its center. Now there's a couple tricks to this. So one thing, we know that the moment of inertia is equal to the integral of r squared dm. That's how it's defined. Now in this case, okay, the r squared part, that's fine. That's kind of going to be the length. The only distance we have here is really the length of the rod, so we can find that. Now the dm is a tricky part. We want to know, how is the mass of this rod changing as you move along its length. So to do this, we're going to use an idea that's very much like density. So if you remember from chem class, density is mass per volume. And we can write the mass of an object as the density times the volume. It's a different way of writing mass. Now this is because this is a three-dimensional object. We want the volumetric mass density. That's what rho represents, or density represents. Well, we have a one-dimensional object, just a rod, so we can actually write its density a little bit differently. We can say the linear mass density, which I'm going to use the letter lambda for, is equal to, instead of the mass per volume, it's going to be equal to the mass per length, or m over L in our case. And if I use that, I can again solve this for the mass, and I can say, well, the mass then equals the linear mass density times the length, and a really small piece of mass, a dm, is going to be equal to the linear mass density, because if we're assuming our object is uniform, its density is constant, times a little small length. And what's going to be nice is I can use this fact, and I can substitute it into our integral, and it'll give us now an integral in terms of the length of the object as opposed to in terms of the small change in the mass of the object. And again, in our case, our dl is really the same thing as dr. So I can even say that dm equals the linear mass density times dr. If I substitute this into our equation up here, this becomes the integral of r squared. Now wherever I see dm, I'm going to put this down there, lambda dr. And since lambda is a constant, this actually becomes lambda times the integral of just r squared dr, which is not a difficult integral to do. Now the only other thing we have to think about is, what are our limits of integration? So we want to integrate along this entire length. Now we could do this two ways. I could start down here and integrate all the way to the other end. So in this case, I'd be integrating from negative, since it's with respect to the center of our rod, I'm going from negative L over 2 to positive L over 2. That's one way I can integrate this. I could also split my rod in half. And the reason that's a little bit helpful is because the center of the rod we're counting as a zero distance, and I can say I'm going from 0 to L over 2, and then just when I'm done, whatever that moment of inertia is, I can use the fact that, well, the moment of inertia of a kind of complex object is the moment of inertia of each piece added together, and I can say this is really two rods from the end to an edge, and I can integrate from the center to an edge, and then the center to the other edge, or center to the edge, and just take it and multiply it by 2, or add two of those together, and that will give me my total moment of inertia. So either way, it will give me an answer. I like doing integrals where one of the limits of integration is 0, so I'm going to use my little trick where I go from the middle to the edge and just multiply it by 2, because we have a nice uniform rod that's cut directly in the middle. So I'm going to use that. So I'm going to say I want to take the integral I'm trying to do is the moment of inertia is going to be the integral from 0 to L over 2, from the center of our rod to the end, of lambda r squared dr, and I'm going to find that and just multiply it by 2 at the end. This is a pretty straightforward integral. I can pull the lambda out. So this becomes lambda. Now the integral of r squared dr is just r cubed over 3. And this is evaluated from 0 to L over 2. And now all I have to do is just plug in my values. One of them is going to be 0. The other one is going to be equal to, let's see, lambda L over 2, the whole thing cubed over 3. And see, L over 2 cubed is going to be L cubed over 8 divided by 3. That's L cubed over 24, so I have lambda L cubed over 24. Now, that's not looking like what they want me to do. Once our answer is supposed to be ml squared over 12, well, I need to get the m back in here, so now my last step can be, I can take my value for lambda over here, and I can sub that back into here. So this becomes now, so lambda is m over L times L cubed over 24. You can see one of the L's drops out. And I get ml squared over 24. Now this is a moment of inertia of one side of the rod, so I want the total moment of inertia. So that's just going to be 2 times the moment of inertia from the center, which is 2 times ml squared over 24. And I get my answer that we've been looking for, which is just the moment of inertia of this rod about its center is going to be ml squared over 12. And again, the big trick about this is just realizing that you can write the mass in terms of the linear mass density, substitute it in so you get a dm, which is now turns into a dr in this case, allows you to actually integrate it easily, and then when you're done, just substitute that linear mass density back out to get the mass back into the situation. And you have your moment of inertia with some pretty straightforward calculus. Now the second part of this question asks you to find the total moment of inertia when you take our rod and you add it to this ring around the outside. So we know the moment of inertia of our rod is ml squared over 12. We just found that. The moment of inertia of a ring we know is that's like, because all the mass is on the outside, is just mr squared. Now in this case, r happens to be L over 2, so we just got to make sure we don't forget about that. And we can only use the fact that the moment of inertia of a complex object is just the moment of inertia of each piece separately. So it's the moment of inertia of the rod plus the moment of inertia of the ring. So we can just add these together. So we have 1/12 ml squared plus, now we have m, and since r is L over 2, so we have m L over 2 squared. So that becomes 1/12 ml squared plus, let's see, L over 2 squared becomes a fourth. So 1/4 ml squared. Well, 1/4 is really 3/12. So 3/12 plus 1/12 gives me 4/12. Well, 4/12 is a third. So my total moment of inertia ends up being just 1/3 ml squared. And again, moments of inertia can be a little bit confusing, but once you realize what they really are, and that you're not going to see any of them that are too difficult, they're usually going to be symmetrical or one-dimensional or something pretty simple. They're not too difficult to deal with.